Okay, so I want to start with some linear algebra. So let M just be a free finite rank ZP module. Okay, so it's just ZP to the n for some integer n. And let U be just a continuous linear operator. Continuous linear operator on M. So in other words, if you choose a basis, it's just a matrix, n by n matrix with coefficients in ZP. Then you can do the following with this operator U. You can define E, which is the limit as n goes to infinity of U to the n factorial. So you have a certain operator, this exists, and it is a projector. So a projector means that its square is equal to itself of E, or rather of M, onto the subspace, well, the subspace EM, which is the maximal subspace on which U is invertible. Okay. I'm not going to prove this. It's essentially pretty easy. I mean, you should think about it as follows. So you have a matrix. Then if you take a sufficiently large power of that matrix, it will be congruent to 1 mod P. And so then you can imagine it, there's parts of which has generalized eigenvalue 0 and parts which are generalized eigenvalue 1. And then as you just take larger and larger p-powered powers of it, the ones go to 1 and the things that are 0 mod P go to 0. So this is just a convenient way of breaking it up. You don't really need n factorial. It would be sufficient to, for example, have just sufficiently large powers of P times some fixed constant, which is, say, the order of GLN FP. Okay. So with that in mind, let's consider the following. So now let's suppose that we have our space of ordinary modular forms of weight K. So this will be, say, p-adic. Sorry, I said ordinary, I meant p-adic. P-adic modular forms of weight K. So on this, we have an operator UP. So this is over ZP. We have an operator UP. Well, of course, this is not a finite dimensional vector space. But nevertheless, it turns out we can do the same construction. So this is a theorem. So it requires something more than linear algebra. It's due to Hitter. I mean, Hitter's theorem can be written in a quite different form, but this is certainly a consequence of that. Is you define EP to be the limit as n goes to infinity of now our operator UP to the n factorial, and it satisfies exactly the same property that as what happened in the finite dimensional space. This is a projector of the space of p-adic modular forms onto the subspace where U is invertible, where UP is invertible. So this theorem is still continuing, so I should put moreover. I mean, it's actually much stronger that we have the following properties. So if you take the dimension of the projection of these forms onto this space, so this is the part on which U is invertible. This is a finite dimensional space. So this is infinity. Moreover, it only depends on K modulo P minus 1. Well, maybe modulo 2 if P is equal to 2. Okay, so this is if P is 2. So it's a finite dimensional space. Not only that, if the weight is at least 2, so if we're in a situation in which we kind of have classical modular forms of interest, then these forms are actually included inside the classical space of modular forms, but now of level P. ZP. Okay. So for example, we proved this space on the right was included inside the p-adic modular forms. This projector actually pushes us back inside this classical space. So this certainly implies it's finite dimensional, because the thing on the right is finite dimensional. Okay. And then what one sees is that this space here, and in fact both of these spaces, these can be decomposed into eigenspaces, well, say eigenforms, for all the Hecke operators TL, L not equal to P, and the operator UP. So in other words, you take a projection of a form, then you can write it as a finite sum of eigenforms for all the Hecke operators TL and UP. And when I say that, well, of course that's somehow known in this classical space, but this is also true somehow for any K. We don't have to be in a situation in which the forms are classical. Even in negative weight, this finite dimensional space has a nice basis of eigenforms. So the first thing to remark is that this implies many congruences. All right. So we can think about it as follows. So let's just take an F. That's a modular form. That's a p-adic modular form. So I can write F as A plus B, where A is just the projection of F onto the ordinary space, and B is, well, F minus A. Okay. So on the one hand, we have A is a finite sum of eigenforms. On the other hand, we have B, well, it's in the complement of the space in which U is acting U is acting invertibly, so U is acting the opposite of invertibly. So what does that mean? Well, it's acting in a way that's topologically nilpotent in the sense of if you iterate U on B, it just has to be getting smaller and smaller. So what that means is that M, if you keep applying the operator U to B, this is converging to 0. Converging p-adically to 0. And so you just immediately get a congruence between UMF. Well, it's therefore converging to just UM of A. And of course, A is a sum of eigenforms, but it's a sum of eigenforms also for the operator U, well, maybe I should say UP. So this is just taking the sum of eigenforms and applying some eigenoperator to it, so they're just all being multiplied by some corresponding scale. So you get, this is literally just some congruence between maybe not literally F and A, but the iterates of U of F on the iterates of U of A. So you might ask, well, something about, well, you might ask, but not until I give you another example. So let's do an example. So let's take the function j. Well, all right, this has a pole at infinity, so it's not literally a p-adic modular form, but you can think about it as, say, a meromorphic p-adic modular form, and we'll see that the theory is pretty insensitive to having poles at the cusps. So what we first do, so first we apply the operator u, j, and we can think about this. This is now, well, even just thinking classically, this is a meromorphic function on no longer the modular curve, but now the modular curve of level 2, because you've increased the level by applying this operator. But it's certainly a function, so let me just draw x02. It's a curve of genus 0. There's a point here at infinity and a point here at 0. And you can imagine, well, what's the ordinary, and well, remember we also have this picture here. This is how x01. So let's recall the picture here. For p-adic modular forms, we removed some supersingular disk. This was the disk in which J was just congruent to 0 mod 2. And then we somehow pulled this picture back. Elements in this region here, because they are ordinary, we could construct a subgroup of index P, which gave us a point on x02. Just to draw the picture again, it'll look something like this region here. So this region will coincide with this region here. This will be some ordinary, again, this is a Riemann sphere minus a disk. So this space here is just a disk, and you see that region there is also a disk. But on the other hand, let's think about the function uj. Well, it's certainly a function on x02, but you can just check by looking at the Q expansion that u of j, well, it certainly has a pole. It has a pole here, but uj has no pole here. So what's happened is, of course, it's not going to be holomorphic, but it is now holomorphic over the ordinary region. So in other words, we see that uj is a function here that's holomorphic, so it is a function here, so it certainly is now holomorphic to adic modular form. So now let's take f to be j, and let's just apply this projector and see what we get. So let's apply here this projector, u2 to e of j. So it has to lie inside some finite dimensional space of the weight 0 ordinary modular forms. Again, here we have level 1. And here maybe over Z2. So we're inside here, but it's inside some small space. So what's the dimension of this space? Well, I told you the dimension is only going to depend on the weight. Well, in this case, the weight mod 2. Moreover, if the weight's at least 2, it has to be classical. So therefore, if you change the weight from k equals 0 to k equals 2, you can do a computation. So E2 of weight 2 has to be included inside the classical forms. I wrote S, but I really mean, I'm not saying has to have a cusp forms. So modular forms of weight 2 and level gamma 0, 2 has to be included inside here. Well, that's not a very big space. It just has an Eisenstein series, and that's it. That's one-dimensional. So what that says is that this ordinary space is exactly one-dimensional in weight 2, so therefore it's exactly one-dimensional in weight 1. So the ordinary projection of uj is one-dimensional. So what is it? So you have to come up with an eigenform in weight 0 that's ordinary, and there is such an eigenform, it's 1. You apply u to 1, you get 1. So the ordinary projection, if you take the ordinary projection of uj, you get 744. Okay, that's just the constant term. So what that says, it says that uj equals 744 plus, okay, uj minus 744. All right. But now if you just keep applying powers of u, well, you can see how to apply it to 744 plus something that's just tending to 0 two-adically. And so what is this? This is just a congruence for the coefficients of j modulo higher and higher powers of 2, as long as you're taking Cn, where n is divisible by higher and higher powers of 2. It says all those terms, as long as n is not 0, will be converging to 0. So that's exactly a congruence. Okay. So in other words, explicitly, Cn tends to 0 if n tends to 0 in Z2. And of course, you have to rule out n equals 0, not for any special reason, but for the fact that there's an ordinary part that you have to keep in track of. All right, so that's nice, but there's something perhaps a little bit unsatisfactory about such a congruence. Namely, you might ask, what's the rate of convergence of this error term? And unfortunately, if we just stick to p-adic modular forms, you can't really get any good bounds on the error terms, just not because it's difficult, but because you can find forms that are sort of in the kernel of this projector, which converge to 0 as slow as possible. As long as they converge to 0, you can find things that can converge as slow as possible just by explicitly writing down some examples. On the other hand, if you explicitly look at J or many other examples, you tend to observe you actually get a linear convergence, which is somehow much better than you might have a hope to expect from these arguments. So what we need to do is to restrict to a smaller class of functions which avoids these pathological things that are converging very slowly. And such things are exactly coming out of the theory of overconvergent modular forms, which are, they're all p-adic modular forms, but there are fewer of them. So that's what we're going to talk about now, which is overconvergence. All right. So first, I have to remind you for p-adic modular forms of a crucial fact, which is that we understood modular forms of level gamma 0p to be inside the space of p-adic modular forms. So we had classical forms of level gamma 0p. We saw these inside p-adic modular forms. And what was the reason for this inclusion? The key point was that if E was ordinary, then we could come up with a canonical subgroup P inside the P torsion. And that gave us a way of moving from a point on x0 to a point on x0p, because we just had the subgroup. So we know we can't do this for all P, otherwise x0 would map to xp, x0p, which is geometrically impossible. But we still might be able to do things with things slightly beyond ordinary. Okay. And that's exactly what we do. So I want to kind of first do a very explicit computation for p is equal to 2, just to show that this is sort of a very concrete thing, and then I want to just make a quick formal remark about doing things in general. So let's just imagine we have p is equal to 2. Let's just take, say, a finite extension of Q2 with ring of integers O and some maximal ideal. And let's now write down an elliptic curve over O. So an elliptic curve over K, in other words, that also has good reduction mod 2. So we know that we can write all such elliptic curves in Weierstrass equation. And since we want to be careful about the reduction mod 2, let's actually write it in the full Weierstrass form like this. Let me remind you, for example, that A1 mod 2 is equal to the Hasse invariant. All right, the Hasse invariant is not a function, it's a section. It depends on some other choices. What choices are there? There's a choice of differential. But of course, when you have a Weierstrass equation, you have that differential. So this makes sense. All right, so all I want to do is to say, can I find a canonical point of order 2 on this elliptic curve? And the reason why I'm doing 2 is because you all know how to compute points of order 2 on an elliptic curve. You write y squared equals a cubic, and you solve the cubic. All right, so you also hopefully know how to complete the square. So let me do that now. So of course, we're only thinking about finding a canonical 2 torsion point, even just over K. So we're allowed to at this point, write it like this. It's x cubed plus a2 plus a1 squared on 4. X squared plus a4 plus a1, a3 onto x plus a6 plus a3 squared on 4. Excellent. So we just need to say, well, is there a canonical root of this cubic? All right, well, of course, if we think about these as just formal variables, no. So we want to have some extra information. So let's try and put some facts in that we know. So we know if we have an ordinary elliptic curve, we're in good shape. So we can certainly assume, although we don't really have to, that A1 is not a unit. Because if it was a unit, then it would be ordinary, because it would be the Hasse invariant. That wouldn't vanish. So you can also check that the coefficients are, I believe it's A3, actually has to be a unit. Thank you. Yes. Fortunately, I'm only worried about this cubic, so my computations have not all turned into dust. Right? If we're assuming A1 is 0 mod 2, if it's supersingular. If A3 was also 0 mod 2, if you reduce this equation mod 2, you would have y squared equals a cubic. But in characteristic 2, y squared equals a cubic has bad reduction. So we're allowed to assume that A3 is a unit. So why is that useful? Well, what are we trying to do? We're trying to find a canonical root of this cubic equation. So how could you possibly do that? I mean, if it was somehow irreducible, you'd probably be in bad shape, because Galois automorphisms would say you can't distinguish them. So how do you distinguish roots of a polynomial over a local field? What is there a way to measure about these roots? You can measure their valuation. So let's compute the valuation of the roots of this cubic, and maybe there's one root that has different valuation from the others. And if there's canonically a root that has a particular valuation different from the others, then that will give us a particular point of order 2. So how do you compute the valuation of a cubic? You compute the slopes of the Newton polygon, and we can do that simply just because we know we have the forms on the right, and we can sort of compute it in the easiest way. So let's do some cases. Case 1, let's suppose the valuation of A1 is at least 1. Then every term is integral except the A3 cubed, A3 squared on 4. So the Newton polygon you get looks like this. You don't know what's going on here. Well, you have something here, you have something here, but the main point, you have something at 3 minus 2. And so this is the Newton polygon, and it has slope minus 2/3. And in particular, nothing's jumping out from this diagram that suggests there's a way of coming up with a canonical element of order 2. So now let's do case 2. So now 1 is bigger than the valuation of A1. It's say bigger than 0. So now if we do the computation, so still we have something at 3 minus 2 coming from the A3 cubed on 4. But what are the other terms that could have negative valuation? Now if A1 has valuation less than 2, A1 squared on 4 will have negative valuation. So we can explicitly put in what the valuation is. If I call this, say, eta, this will be the point 1 times 2 eta minus 2, and this will be the point 2 eta minus 1. And so now it's going to depend exactly what eta is. Somehow if eta is low enough, what we'll see if we look at the Newton polygon is it will consist of 2 pieces. So in this situation here, we really have a situation in which we have 2 roots which have the same valuation, and another root that has a unique valuation. So in particular, where you can do the computation, it's linear algebra, as long as eta is less than 2/3, there will be a unique root which has valuation different from the others. So if this is less than 2/3, we could find a canonical point of order 2. All right? And of course, you can continue this picture somehow by continuity, and also by computation to see what happens if you just wanted to do, say, eta is equal to 0. Then you would have the following picture. It would look like this. Okay. This would be 3 minus 2, and this would be 1 minus 2. But again, you would have a unique thing here, which would give you a point of order 2. So what that says, and what we've basically proved, is the following theorem. if the valuation of the Hasse invariance of the elliptic curve is less than 2/3, then there exists a canonical point or the canonical subgroup of E2. So let me just say a little bit about that. Here I'm taking the Hasse invariant. The Hasse invariant is just A1 mod 2. So if you think about A as in characteristic 2, or you lift it to characteristic 0, its valuation makes sense as long as the valuation is less than 1. Right? 2 to the 2/3, you can tell has valuation 2/3 even when you reduce it mod 2. Any power of 2 higher than 1, you can't quite tell, but at least in this range, the first thing makes perfect sense. And in that situation, you just look at the the cubic, and you have a particular two-torsion point of unique slope. And just looking at this picture here, you can see it agrees with what we had in the previous case. In this case here we have this point of order 2. These points of order 2 have slope 0. So you can think about that as meaning when you reduce those points mod 2, you can actually reduce the mod 2 and get 2 separate points. But that's what we expect, because in the ordinary case, we were taking the kernel of reduction, and then we reduced mod 2, we were getting the points over F2 bar. Of course, in all the other cases, when you reduce mod 2, in terms of reduce mod the maximal ideal, everything somehow disappears in the supersingular case. But we're doing more than just reducing the maximal ideal, we're reducing literally 2 to the power of 1. That's somehow thicker than just reducing mod the maximal ideal. Okay. So you have a canonical subgroup. Canonical. All right. So let me also just say, I should, before I mention what happens for general P, you can also imagine a formal computation in which you are trying to do this. If you think about what these objects are, these are somehow Newton polygon of this p-torsion subgroup, and you can imagine, especially if these coefficients are vary in some nice way, that this Newton polygon will vary continuously. And so therefore, if we have a region like this with a Newton polygon that has a really big bump, and there's a canonical way of choosing this kernel of reduction, even if you move it to a point in which it's not ordinary, it can't suddenly snap from something like here to a straight line. So in fact, just by formal reasons, you know that you can extend beyond the ordinary locus and still have a canonical subgroup. But that's not, okay. All right. So what do we do with this canonical subgroup? Well, now what we can do, well, so let me first, I guess I should mention somehow the more general statement. So what we're somehow imagining is, previously when we had the ordinary locus, we could think of a point on the ordinary locus on x01 and pull it back to a point on x0p. So now what we can do is for at least not all supersingular points, but at least some points in characteristic 0 which reduce the supersingular points, whose Hasse invariant is not too small, for those things, we can still extend it and pull back to x0p. So here's just a diagram of what's happening for x037. I just wanted to put it together and say a little bit about what's going on. So here, what do we have on the bottom? This is just x01. So and it's the Riemann sphere. It has some points, you know. It has there's the cusp. There's the point where j is 0 and j is equal to 728. They're both ordinary. And then it has these 3 supersingular disks that are kind of bulging out like this. And you can imagine this is just a picture which you can reduce to, of course, the special fiber, which is just some nice P1, and it has these 3 supersingular points. And these blobs are just a reduction of these things. Now, it's not the case that for all of the points in these blobs, we can find a canonical subgroup, but as long as we're not too far into these disks, so as long as we just go a little bit into these disks here, those points here, we can somehow find a way of pulling it back to x0p, which is here upstairs. And I'm just sort of drawing this picture geometrically. Of course, this will have genus 0, this will have, in this case, genus 3. There's no way we could somehow keep pulling the things back for just topological reasons. So somehow we know we can't do this at all, but at least we can do it a little bit further. Of course, there's some cheats going on in this picture because it's really, I mean, non-Archimedean fields are hard to draw in general. So there's a problem. So what we can then do, we can define now a space of overconvergent modular forms of gamma, and now let's include a radius r. So now this is going to be as follows. So now this is maybe a little bit informal. So what we do, so instead of taking sections over the ordinary locus, we take sections over all of the elliptic curves for which the Hasse invariant has valuation at most r. So I'll call this x of r and omega to the k. So if we're imagining p is equal to 2, well, so here this is the region where the valuation of the Hasse invariant is, say, at most r. So for example, x0 is just the ordinary locus. So in fact, again, because the Hasse invariant is defined mod p, this makes sense as long as r is well, less than 1. Right? If you start making r bigger than 1, it doesn't quite make sense to talk about the valuation of the Hasse invariant if it's bigger than 1. So you have these various regions, and there's somehow so far that you can go. All right. So here's an example. Again, an example I've said before. So again, x01, here we have this, and x02 is this region here, and here's the ordinary locus, and then we can start continuing some way into the supersingular locus. So in both these cases, these are curves of genus 0, so they both have uniformizers. A particular uniformizer for x02 is given by the function f, is the product of n equals 1 to infinity of 1 plus q to the n to the 24. Right? So previously we said, well, p-adic modular forms are just functions over this. This is just a ball, so they were just power series, in fact, in J inverse. Right? So two-adic modular forms. These were just functions somehow for J inverse less than or equal to 1, which were just power series, say, in J inverse that converged. So, well, in that, sum of a(n) to the j to the minus n, such that a(n) tends to 0. So they're just functions on a disk. Now, what are these guys? Well, again, we've just extended further into x02, but we haven't gone all the way. So it's still just a disk, but it's just a bigger disk. Okay, and so in fact, what it will look like, well, instead just be functions of J inverse less than or equal to 1, it'll be functions on a smaller disk, J inverse, for example, less than or equal to, let's say, some power of t, where somehow t is bigger than 0, which again will just be power series, but instead of power series in J inverse, it'll say be power series in J inverse times some small power of p. Well, p is 2 here, of course. So as formal spaces, one's functions on a disk, one functions on a slightly bigger disk, they don't look so different from that perspective. So what do we gain from just extending our p-adic modular forms to overconvergent modular forms? Or in other words, restricting the space of functions on the disk to the functions that converge a little bit further. Where's the beef that we get by knowing that things converge a little bit further? And the real point is as follows. So again, we can still think about what's happening in characteristic 2. It doesn't really matter. So if you imagine we have an elliptic curve, then it has a bunch of subgroups, well, P, Q, and R, say, of order 2. So there are 3 points of order 2. So there are 3 possible subgroups. So what we can do with these elliptic curves in this point, we can form the elliptic curves E modulo P E modulo Q and E modulo R. So let's suppose that the elliptic curve E, its Hasse invariance, had valuation eta. Then you can ask, what happens when I take the quotient by these three things? So what happens, here's this table, what is the valuation of the Hasse invariance of these guys? Well, let's suppose that the elliptic curve was actually ordinary. Well, then eta would be 0, but if you take an ordinary elliptic curve and you do an isogeny, it's still ordinary. So if eta is equal to 0, we would get 0, 0, and 0. Okay. But now let's imagine what happens when eta is not 0. Now this is a computation you can do, but I want to somehow do it by a kind of very hand-wavy heuristic thing. Even in characteristic 0, even in the Tate curve, what are the subgroups that we have? So one subgroup is the kernel of reduction, and then the other subgroups are things of which somehow persist when you reduce the mod P. All right, so what is the kernel of reduction? Well, the kernel of reduction, when you reduce that mod P, it's some subgroup of order 2 that you don't see in characteristic 2. But now let's imagine you take an elliptic curve in characteristic 2. What is a kind of isogeny which has no kernel for an ordinary elliptic curve? It's exactly Frobenius. Right? So if I imagine here, let's just say P is the canonical one, and these guys are not, then I can imagine this column here as really being what's happening when I take E and apply Frobenius to it. But what does that mean the other two things are? Well, if it's not Frobenius, because multiplication by P is inseparable, it has to be the dual to Frobenius. So what do you expect happens to the Hasse invariant when you do Frobenius? Well, what happens to Frobenius? You're just kind of, things are being replaced by their Pth power. So here you expect that the valuation is P times eta. And here you expect to get things which are the opposite of Frobenius. So you expect to get eta on P. And in fact, this is exactly the case as long as eta is small enough such that these numbers are somehow smaller than 1. Okay. Of course, I'm writing this with P. It's true more generally. Okay. So what does that mean? And this is really the key point, is that if you take a function which is now over convergent of some radius r, and then you apply u to it, you get, well, an over-convergent function, or over-convergent form, but now the radius of convergence has got bigger. Right? If you take a p-adic modular form, it's a function on the disk, you apply u, you get another function on the disk. If you have some radius of convergence that goes beyond the disk, and you apply u, what happens is it gets more convergent. So literally, well, it's the minimum of p times r, and there's a point which you have to be careful, which is about p on p plus 1. But if you imagine, for example, that r is small, you're really getting something big. So somehow, why is this true? Well, let's just imagine that we want to apply uf to an elliptic curve. And let's, to do the computation and make our lives simpler, let's just imagine we're in weight 0, so we don't even have to remember the differential, which will just kind of add some complications. Okay, so what's the definition of that? Well, how can we define, so what is the definition of this? This is the definition of the sum of f of E divided by the P for the P not equal to the canonical subgroup. Okay. So in order for this to make sense, the elliptic curve better have a canonical subgroup, and that's kind of why this P on P plus 1 is there. That's the analog for general P of what we had as 2/3. If P is 2, you see you get 2/3 in that case. So as long as we're not beyond that point, we have a canonical subgroup. Okay. And so what's the point here? So the point is, this F is only defined for things, for elliptic curves, which the Hasse invariant has valuation at most r, but now we want to evaluate it on elliptic curves whose valuation is bigger. So now we can imagine, say, the valuation of the Hasse invariant of E is, say, I mean, it could be bigger than r, but as long as this is less than, for example, PR, well, when we take the quotients by things that are not canonical, what will happen is that the valuation of the Hasse invariant of these guys will be less than or equal to r. So even though we can't apply f to this elliptic curve, because the Hasse invariant is possibly too big, when you quotient out by these subgroups that are not canonical, they move towards the ordinary locus for which f makes sense. And so then you can apply it. And so then, in other words, even though f doesn't necessarily make sense, UF makes sense. Okay, so that means that U gives an operator from MKR. Well, it maps to now functions on this bigger disk. Let me ignore this P on P plus 1. And then, of course, you can just restrict. If you have a function on a big disk or a section on a big disk, you can certainly restrict to the smaller disk. So that's an operator that we now have. Okay. And so this is the key point, is that when you restrict functions from a bigger space, say a big disk to a small disk, that turns out to be a compact operator. And in particular, therefore, when you have this operator U, you deduce from this that U is a compact operator. So therefore, U is a compact operator. Just to give an example, let's suppose that CR is, say, just, say, complex analytic functions with radius of convergence F at most R. Then here's a function from C1 to C2. You take a function and you replace it by, say, Fz on 2. If Fz has radius of convergence 1, Fz on 2 has radius of convergence 2. Okay, and now you can just restrict this to C1 by restricting this to F of Z on 2. I mean, just the restriction map. So you have an operator on the functions of radius of convergence at most 1 that just takes a function to F of Z divided by 2. And so because this restriction map is compact, you deduce that this map has some very nice properties. And in particular, it has a nice spectrum. And in particular, in this case, of course, you can see that there's a basis 1z, z squared, z cubed. These are all eigenforms for this operator. And moreover, any function in C1 you could write as a sum of eigenforms, just because it's given by some power series. So, well, of course, that's this example. You might ask if we could get the same thing in general. And if we did, what would that say? So hope, again, is that the compactness of U implies the following. Given an F that's over convergent, that you can write F as a sum, now I equals 1 to infinity, with these phi I are now eigenforms for the operator UP, and because you now have a nice Hecker option, and for TL, for L not equal to P. Moreover, if you apply U to these guys, you'll get, there'll be eigenforms for U, and you'll have some spectrum, lambda 1, lambda 2, lambda 3, etc., where these eigenvalues are becoming more and more divisible by 2. So this is somehow a massive generalization in some sense of the ordinary projection. The ordinary projection is somehow writing F as a sum of things whose eigenvalues is a unit plus something else. Here we'd really like it to write it as a sum of all eigenforms in some convergent way, such that each of the eigenforms has a higher and higher valuation of these terms. In other words, smaller and smaller slope. Okay. And so if we had that, in some sense, this would really, for such an f, tell you everything about the congruences of f modulo any powers of p, and also about the congruences modulo f if you iterate it under the operator u. Okay. So what is the snag? The snag is that if you have a compact operator on this space, it's not immediate that you can really always expand things out in an eigenbasis like this. So this space of modular forms, so it has a nice norm, and so it certainly makes sense to talk about U in terms of acting on, say, a Banach space. But usually, if you want to, say, diagonalize an operator, you want it to be self-adjoint. You want it to act on a Hilbert space. But there are no p-adic Hilbert spaces, just because, well, if you try to think about what a Hilbert space is, you need some kind of positivity. But it's hard to have, there's no real notion of what it means to be positive p-adically. So you have to worry that maybe your operator U, for example, if you think about it as a matrix, might look something like this. P squared dot dot dot. Here's an operator such that all the eigenvalues of U are just 0. It's lower triangular form, so it's also hard to see all the eigenvalues are 0. And this U, what happens if you project it? It just gets very small very quickly. But there are never any eigenforms. So somehow it's as if everything in U is really, if not in the kernel, but somehow topologically in the kernel. It's just the way the powers of U grow, it grows faster than any power of P. It grows, in fact, to some quadratic power of P, but yet there are somehow no eigenforms for this. So instead, the only thing one can do formally is, namely, you have the following. You have an asymptotic expansion. So given f that's over convergent, there exists an asymptotic expansion in this form, alpha I, phi I. So it's exactly the expression we had here, but now it's asymptotic. So what does that mean? Well, it means the following. Essentially, if you say fix an integer h bigger than 0, and you take f minus the sum here of the eigenforms, but you just do the big eigenvalues. So this bigger than, say, p to the h. Sorry, smaller than p to yes, bigger than p to the h. Okay? So in other words, if you take some finite cutoff, and then you apply powers of U to that, well, then it grows faster than p. It'll grow faster than some linear term, which will be p to the OH. So I realize I'm over time, but I just want to give one example. And I'll come back to these examples next time. But I have the following example. So let's take, for example, the modular form 1 on eta, which is q to the minus, I think, 1 on 24, times the sum, n equals 0 to infinity, of, say, Pn q to the n. Well, this is half integer weight, and I've been talking in some sense about things of integer weight, but really the theory works perfectly well, modulo just a few natural translations into this setting. And let's take, for example, a prime p, which I'll just take to be 5. Then what does this say? Well, again, just like with J, it's not holomorphic at the cusp, but once you apply U, you kill off these terms from the cusp. So you have the following. If you apply U to 1 on eta, so this operator U now is really what you might call U of P squared, then you should be able to write it. It has an asymptotic expansion as follows. So I'll write it like this. Alpha 2, phi of 2, plus alpha 7, phi of 7, plus alpha 9, 5, 9, plus dot, dot, dot. So what are these guys? Well, phi k, it's an eigenform for u equals lambda k times phi k, but the size of lambda k is equal to p to the k, where p is 5. So what happens, for example, is if you start applying the u operator, the dominating term is this term here, and so this, each time you apply u, you'll pick up a factor of 5 squared, and so when you iterate u, it'll just be divisible by 25 to the n, and that exactly relates to a congruence of Ramanujan that explains why when you look at the congruences module, maybe it's not proved by Ramanujan, but I guess you didn't prove very much. If you look at P, if things divisible by certain powers of 5, they'll be divisible by the appropriate power of 5 coming from this term. But it says more than that. It says that the main term contributing to these partitions will be exactly this eigenform, which will now be an overconvergent eigenform. And just like a usual half integer weight, its coefficients should be related to p-adic L values. And again, its Shomorek lift should correspond to various Gauss representations. So you have something like that, but you'll even then say something about the next term, which is somehow much, much smaller. You only see that modulo, say, powers of 25 to the 7, but et cetera, et cetera. And this, in some sense, well, if you could upgrade this to an equality, you would, in some sense, have a formula that explains the congruences for the partition function, at least, let's say, n congruence, probably something mod 25, modulo arbitrary powers of p in terms of all these eigenforms. So what we'd like to do next time is to say something about, can we upgrade this to an equality? And also, if you care about, say, congruences, or you care about this expression, what can you say about these mysterious eigenforms that are non-classical? Like, what type of properties do they have? And so I'll talk about that in my second talk later on today.